Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem brothers from different roots. This is an easy level question and it's the problem of the day on Geeks for Geeks. Similar sort of question has been asked by Amazon and this is a follow-up of that question. So let us go through the question now. Given two BSTs containing N1 and N2 distinct nodes. Okay, so this is a point to be noted. BSTs will only have a distinct nodes in this case. So whatever the nodes that you'll be finding in BST1 or BST2, all of them would be unique, right? And given a value X. So I also like to mention, so if you are finding 8 in BST1, there's a chance that you can even find 8 in BST2, but you will not be finding 2 or 3 8s in BST1 or BST2. Only single 8 would be there. That means distinct elements among that particular BST. So, and given a value X, okay, so your task is to complete function count pairs that returns the count of all pairs of A comma B, where A belongs to one BST and B belongs to another BST. Great. So A can be from BST1 or BST2, and if it's from BST1, B must be belonging to BST2. And if A is from BST2, B must be belonging to BST1. Okay. So that A plus B equal to X. So this is the target that you need to get. So X is the target. Like you need to add some elements from BST1 and then BST2, and then you need to have X. So you need to find all the pairs that are possible like this. So these are some of the examples that have been given. We'll see that in brief. And expected time complexity is O of n, auxiliary space is O of n. Indeed, we are using the same, but you might find many solutions using recursions or map or something else, but we will not be using all those stuff. I want to make sure I'm putting out the most unique solution possible. I'll be using stacks to solve this. Okay, stacks is what we'll be using to solve this, and in iterative approach, we'll not be using recursion. And we can easily satisfy these conditions, like number of nodes can go up to 10 power 5 and data of node can go up to 10 power 6. Our solution is going to satisfy these constraints. Okay, and the topic tags are yes, traversal, BST, etc. So now let us go through the example. So this is the example that has been given. So 5, 3, 7, 2, 4, 6, 8 and 10, 6, 15, 3, 8, 11, 18. So these are two BSTs, and in this case, if you can see, the X is 16. Okay, so X is actually equal to 16, and what is the output they have given? 3. So let us see that. Why is it 3? So if we carefully observe, if I stand on 5, okay, if I stand on 5, do I have the remaining difference, like 16 minus 5 equal to 11? So this is what I need to search in my BST2. So do I have 11? Yes, I do have 11. So that's the reason there is one pair. Okay, so we'll just write it here. So let us assume as of now our count is 1 because we have found 5 and 11. And now come to this 3. So what is the difference that I need to search for? 16 minus 3, that is equal to 13. So do I find 13 in BST2? No. So this is also gone. 3 cannot be an answer. So like 3 cannot be a pair. Okay. So coming to 7. So what is the difference I need to find? 16 minus 7 equal to 9. So do I find 9 in my BST2? No, I cannot. So this is also not going to be one of the pair elements of the pair. And come to 2. So what is the difference I need to find? 16 minus 2 equal to 14. Do I find 14 in my BST2? No. So I cannot even take this 2. Okay, I cannot even consider this 2. Come to 4. So 16 minus 4, which is actually equal to 12. Do I find 12 here? No, I do not find 12 in BST2. So this is also one. So what's the next thing? So 16 minus 6, that is equal to 10. If I'm considering 6, do I have 10? Yes, I do have a 10. Fine. So I've got another pair. So right now my pair is count is 2. And now coming to another thing. So if I stand on 8, do I have 8 in my BST2? Yes, I have 8. So here it is. So yes, I did find another pair as well. So count is actually equal to 3. So that is the reason output is 3. Okay. So the same pairs 5, 11, 6, 10, 8, 8. So 5, 11, 6, 10, 8, 8. That's what we have found. So that is the reason output is 8. I hope people understood what are they actually trying to ask and what we need to actually give the output. Okay. We just need to give the number of counts, like number of pairs possible. So I hope you people understood. Now let us frame the approach. Great. We'll be using this example itself to understand the approach that we are going to frame. What is the speciality of BST? What's the speciality of BST? So speciality of BST is it is sorted. It is sorted. Where it is sorted? How it is sorted? How do you identify that sorted? If you write the in-order traversal, if you write the in-order traversal, what is in-order traversal? In-order traversal in the sense left, figure out the left and come to the root and then figure out the right? So this is the in-order traversal. What's the in-order traversal of BST1? If you go to the left, okay, I'll be writing with some other thing with left and left. Now you'll be writing first 2 and then come to this particular, like 2 is done, come to 3, write 3 is done, and then come to the right 4. Okay, now because this whole left part is done, now come to the root, that is 5, and now come to the right side. Now come to the right side. So this is 7. So go to the left again, 6. So 6 and then come to this 7 and then come to this 8. So do we find this particular thing to be sorted? Yes, we got a sorted array 2, 3, 4, 5, 6, 7, 8. So this is an increasing order. So and this represents the BST, isn't it? Because in BST, what is the rule of BST? All elements to the left are less than roots data, and all elements to the right are greater than roots data. Okay, so how do I write this? Yeah, great. I can write this in this fashion. Roots data greater than roots data, isn't it? Greater than roots data. So that is the reason we are getting a sorted thing. So why can't we use this particular approach? Why can't we use this particular like property of the BST to solve this question? So what am I saying is, let us assume you are given an array. Okay, you are given an array, and there are some elements like this, and I say that these elements are in increasing order. Okay, these elements are in increasing order. And I'll say there's another array as well. So this is like this. So these are elements are in also increasing order. So if I come from this direction, from right to left, it would be decreasing order, isn't it? So this is also increasing order from left to right, but decreasing order from right to left, isn't it? The same thing. So even if I say that, look out for some target X, such that like if A belongs to this array, B belongs to this array, so A plus B must be equal to X. I'm telling, check for any A so that it has B, so A plus B will be equal to X. So that's what I've told. What is the approach that you'll be doing if I will giving you these sorted arrays? So you'll be standing on this particular position first, and then this particular position first. You'll be checking. So if I say like here there is X, here it is Y. So first you'll be checking the sum of X and Y. So X plus Y. And this let us assume this is some K. Okay, X plus Y, A plus B must be equal to K. And now X plus Y you have done. If X plus Y turns out to be equal to K, then you'll be increasing your count, isn't it? You'll be increasing your count plus plus. Count plus plus is what you'll be doing. But what if this X plus Y turns out to be less than K? X plus Y turns out to be less than K. Then you'll be going to the next element of X, because you'll be looking out for some element that is just greater than X, so that your target would be equal to like your sum would be equal to the target, isn't it? That's what you'll be trying to find. So now you'll be coming to this particular position. So you'll be iterating towards right. Where the elements are in the increasing order from left to right. I mean in the first thing. Okay, in the first array. Let us assume your sum turns out to be greater than K. What will you do in that case? Come to the left here. So that you'll be finding some element that is less than Y. Okay, that's less than Y, so that you can get some sum that can be equal to K. That's what you'll be in an intuition, right? That's what you'll be assuming. So you'll be coming to the left. So once if you find the sum to be less than K, you'll be going towards right side in the array that you're following, like in the increasing order. And if the sum turns out to be greater than K, you'll be going to the left that you're following from in the decreasing order. So the same thing will apply here as well. So we'll be traversing from left in the first BST, where we are assuming like we are going to traverse the increasing order stuff, and we'll be traversing from right, where we are traversing in the decreasing order. Okay, so this is the main thing. And if in case we find that to be equal to K, we'll be increasing the count. So how are we going to do that? So I hope you people understood this approach. Like what am I trying to do? This is the blueprint of the approach. We have not used the elements that we have not figured out what are the elements that we are going to use to complete this approach. It's just a blueprint of the approach. Okay, so this is done. So how do you do this? So this is where we use stacks. Okay, this is where we use stacks. So how am I going to use stacks? So consider two stacks like this. Okay, so this is stack 1. This is stack 1, and this is stack 2. Okay, this is stack 2. Fine. Now this is stack 1 and this is stack 2. So what am I trying to do? As said, we'll be going to the, like in BST1, like we'll be writing X equal to 16. This is what we need to find. So in BST1, we will be traversing in increasing order. Okay, increasing order. And BST2 will be traversing in decreasing order. So if that is the case, I need to go to the least element in the BST1, isn't it? What's the least element in the BST1? This is the element, isn't it? What's the greatest element? In BST2? This one. So I need to traverse to this particular points, and if in case I find that they are less than the target or greater than the target, I need to go up and down, left and right accordingly. Okay, left and right accordingly. So what I'll be doing is initially I'll be storing all these particular things in the stack. So because we are following the in order stuff, and we are bothered about the least possible values in BST1 and greatest possible values in the BST2, we'll be doing a leftward traversal in the BST1 and be storing all those nodes in the stack 1. So what do I mean by that? So initially I'll be storing 5. So 5 I'll be storing in the stack, and then I'll come to 3. I'll be storing 3 in the stack, and then I'll come to 2. I'll be storing 2 in the stack. Okay, so this is done. Now what about stack 2? So stack 2, in the stack 2 I'll be storing first 10. So 10 I'll be storing now, and then 15 I've stored now, and then comes to 18. Okay, 18. This is what I'll be storing now. Okay, so this is done. This is what I've done. This is what I've stored. Now we'll be taking the sum of these top elements. Okay, we'll be taking the sum of these top elements. What is the sum of top elements? Okay, I'll just write this stack 1 and stack 2 beside. Okay, so what are the sum of the top elements? So 18 plus 2 is the top elements, isn't it? 18 plus 2 is the top element. It's like this. So as I've told, like we'll be taking two arrays. What is the first step we'll be doing? be on the starting most position of the first array, which is the least element, and be on the last element of the second array. So this is the greatest element. So we'll be taking the sum of these two. Okay, if that turns out to be less, you'll be moving this to here. If this turns out to be high than the target, they'll be coming to this left. So that's the arrangement that we are doing. Same thing we'll be doing here as well. So we have taken the sum of the first two elements, and that it is 20, and that is greater than 16. That is greater than 16. What if it's greater than 16? That means we need to reduce the largest element. So what I'll be doing is I'll be popping this out of the stack. So 18 is gone now. So what is there now? So I'm on 15. Okay, now I'm on 15. So 2 plus 15. But before that, you're on 18, right? You're on 18. So 18 will be looking out for its leftwards elements. Like if I find anything towards my left, because I need to decrease 18, I need to look out for some element that is less than 18. So I'll be looking out for in the left side of 18, because in the left side of 18, what would you get in the left side of 18? The elements that are less than 18. So I'll be checking for the left side of my 18. Do I find any element to the left side of 18? No, I do not find anything. So it's just a null. Okay, it's just a null. So I do not have anything. So I do not need to store anything in my stack to consider. Okay, I cannot store anything in my stack to consider. You'll be storing in the stack, so that you'll be taking the topmost elements and you'll be dealing with them. But you do not have anything that is less than 18 to be in the left side of 18. So you'll not be adding anything to the stack. And what's the next less than element that's less than 18 that's available? 15 only. So you'll be dealing with 15. So 15 plus 2, that is actually equal to 17, and that's again greater than 16. So initially you are on this position, and you are on this position. So this is done. 18 is done. Now you have come here. Again you are seeing that the sum turned out to be greater than 16. So now you'll be checking to the left of 15. Do you have anything to the left of 15? Yes, I have 11. So okay, let me go there. I'll even pop this out. So I'll just pop this out. I'll just pop this out and add 11 to my stack. So when I add 11, what are the topmost elements now? 2 plus 7. So 11 plus 2, that is 13. And this is less than 16. Now I need to look out for some element that is greater than 2. So I'll be like moving, like popping this out, and I'll be checking for the right side of 2. Do I find any element that's right side to my 2, so that I can put it in my stack? So but that's nothing. This is null itself, isn't it? There's nothing to my to the right side of my 2, because I'm looking out for some element that's greater than 2. And where can I find that? To the right side of my 2. But to the right side of 2, there's nothing. So I just need to go up. Okay, so I'll be going to 3. Okay, I'll be going to 3, because there's no element that's right side of 2, and that's only null. So I cannot add anything to my stack to consider. So the only element that's just greater than 2 is 3. So now we have come to 3. So this green will be here. So what is the thing that we'll do now? Now we'll see the sum again. So what are the topmost elements? 3 plus 11. So 11 plus 3, that is actually equal to 14, and that's again less than 16. So what we'll be doing now, because now it turned out to be less than 16, so this also will be popping out, and you'll be checking out to the right side of 3. Do you have any other element? Because you just need an element that's greater than 3. So yes, I find some element like 4. So okay, I'll just add that to the stack. And now I'll be dealing again with the topmost elements. What are the topmost elements now? 11 plus 4 is equal to 15, and that's again less than 16. So now again I'll be checking out to the right side of my 4. So do I have anything to the right side of my 4 so that I can add? I just need some element that's greater than 4, so I'll be checking to the right side, but it's not. So that's nothing. So I'll even need to pop this out, and now what's the element that's there? That's just greater than 4? Only 5. So even done with this now. Now we have come here. So 11 plus 5. 11 plus 5, that's actually equal to 16. 11 plus 5 equal to 16, and that is actually equal to 16. So initially your count equal to 0. Now your count turned to be 1. Okay. Now we have got 60. Now we have got some pair. Now what will you do? Now let us assume in an array, 2 arrays like this you have considered. You are on this position and now you're this position, and you found these 2 elements like sum to be equal. What will you do now? You'll be seeing for another pairs. So for that, you'll be going to the right in the first array and to the left in the second array. So that's what you'll be doing, right? Similarly, we'll even do that here as well. Okay, So once we have got this particular thing, we'll pop this out. Okay, we'll just add the new element. We'll pop this out and we'll add the new elements. 11 and 5 are popped. What is the new element that you're going to add? So you'll be adding, what's the new element that's next to the right side of 5? So that is 7. So you'll be adding 7. I'll just erase all these parts to better reference. 7. And also here 11 is what we have done. 11 is completed. So what's the next thing we have? 10. So I'll just erase these things. Okay, we still have a 10 in the stack. Okay, we still have 10 in the stack. So once we have come to the 7, we will even add 6. Why? Because we are doing the in-order traversal. What is the in-order traversal? Like we need to have, like, left side is first need to be dealt, and then the root, and then the right, isn't it? This is what we need to follow. So once you have come to the 7, there's something that is still less than 7, because in the BST one you're following the increasing order. So for that reason you'll be adding 6 as well. So once you have come to this particular node, you'll be looking out for the leftmost values. What are all the leftmost values that are there? You'll be adding that to the stack, because you need to follow the increasing order. Okay, so now we have come to this particular thing. Now we are on 6, and in the stack 2 you have 2. So you'll be seeing now what are the topmost elements, 6 and 10. So 10 plus 6, that's equal to 16, and that's again equal to 16. So your count has been increased. Now you'll be popping out these two elements again. Now you'll be popping out these two elements. What's the next thing that you'll be adding? As said, 6, right? But do you have anything to the right side of your 6? No. So you'll be having 7 itself in the stack, and for the right side of 10, sorry, in the left side of 10, like you're on this particular position initially, right? So in the left side of 10, what do you have? 6. So you'll be adding 6, and also you'll be adding 8 as well. You'll be adding 8 as well. The reason being, as said, in the BST1 we are following the increasing order. In BST2 we are following the decreasing order. So we need to add the highest elements, okay, highest greater most elements in the stack. So you'll be now on this particular position. You'll be on this particular position now. Okay. So 7 plus 8. This 7 and 8. These are the topmost elements right now. I hope you people are understanding. BST2 follows the decreasing order stuff. So whatever the elements that are greater than at the present node, you must add all of them. So once you have come to 6, now you'll be checking for your right side if you have any greater than elements, because you are following the decreasing order. So 8 is there. 8 is another possibility that's greater than 6. So that you need to consider first. Okay. So you're on this particular 8 now. You're on this particular 8, and we are on 7. So now we'll be checking the sum. So what is the sum? 8 plus 7 is equal to 15, and that turned out to be less than 16. If that turns out to be less than 16, what you need to do? You need to increase the BST. You need to go for the next element. So what's the next element for this particular thing? 7 is done because 7 is not suitable. So what's the 7's right side? 8. So this is what you'll be considering, and you'll be adding it to your stack. Okay, 8 is what you'll be adding. Now you'll be seeing the sum. What is the sum now? 8 plus 8. 8 plus 8. 8 plus 8 equal to 16, and that is actually equal to 16. So your count turns out to be 3 now. So now you have found out 8 plus 8, that turned out 16. Now you'll be even popping out these two. So you find that stack 1 is empty. Stack 1 is the empty in the sense everything has been traversed. No other element is there to add in the stack. So we'll be cutting out from the loop. Once we cut out from the loop, we'll be returning the count. I hope you people understood this. So there's no other element in the stack 1 or in the no BST1 that's still left unexplored, so that you can add that to the elements of stack 2. There's no such element. We have covered all the elements in the BST1. So that's the reason you'll be coming out of the loop, like you'll be breaking out. So once stack 1 or stack 2 gets empty, and then you'll be finally taking the count. I hope you people understood. It's the same thing that we'll be doing when we have got two sorted arrays. First array will be dealing in the increasing order, second array will be dealing in the decreasing order. The same thing we have applied here as well. The same concept we have applied here. So if you are not able to understand, do the dry run once again. Okay. So this is the whole approach. Now let us code it out first. So what's the first condition that you need to write? If root 1, okay, root 1 equal to null, or root 2, okay, root 2 equal to null. So in both these cases you can return 0. Okay, you can return 0. So what's the other thing? Take stacks now, stacks of node pointers. BST1 is what I'm going to take, and BST2, and top pointers, like top elements, top 1 and top 2. Okay, so what is the next thing that you're going to do? And int count also, int count equal to 0. So while true, first thing, whatever the elements that are there in the BST1, what we'll be doing first, you'll be like, I'll just erase all this stuff so that for you'll be getting better clarity. You'll be taking out the least possible elements that you need to take. So you need to have 2 first. So you'll be traversing in the left, because we need to maintain the in-order traversal. So you'll be taking all the elements of the left. So while true, like this root 1 is, while root 1 is still defined as push BST1 dot push of root 1, and root 1 equal to root 1's left. Okay, root 1's left, and similarly root 2 as well. So in root 2 you'll be pushing out the right side elements. Okay, BST2 dot push of root 2, and root 2 equal to root 2's okay, root 2's right. Fine, this is also done. And what's the other thing? Now after this is one of the condition that you need to write. If your stack BST1, okay, BST1 is empty or BST2 is empty. So in both these cases you need to break, okay, because there's no other element that's left to be explored. Okay, so in both of these cases you need to break the loop. So now the other thing that's there is top one is BST1 dot top. So top 2 is BST2 dot top. If your top 1 data plus top 2 data turns out to be equal to x. So if this turns out to be equal to x, what will you do? You'll be increasing the count first, and then you'll be popping out BST1 dot pop and BST2 dot pop. Okay, BST2 dot pop, and the second thing is, now you'll be going to the right side of your first BST1 and left side of the BST2. That's what you'll be doing, right? So your root 1 would be top 1's right, and root 2 is top 2's left, isn't it? So I hope you people are understanding, so there's no sort of confusion. And if in case else, okay, if the top 1 data plus top 2 data turns out to be less than x. Okay, if in case this is less than x, okay, if this is less than x, what will you be doing? First one, you'll be popping the top element, and then you'll be going to the right side. So right side, to root 1 equal to top one's right, top one's right. I hope you people are understand this particular thing. Else if this turns out to be like the sum turns out to be greater than x, so you'll be popping out the in the second stack and then going to the left. Okay, top 2's left, and finally you'll be returning the count. Okay, finally you'll be returning the code. That's it. This is the whole code for this. I hope you people understood. So we are taking the stacks first, we are taking the top pointers. So we are first initially pushing out all the elements in the left of the BST one, like the stack, root 1, and then right side elements all root 2. So, and if in case any of them is empty, that means we have explored all the elements. So break it. So top 1 is called BST1.top, top 2 equal BST2.top, and if the if their sum turns out to be the target, like or x, so count plus plus and remove the elements from the stack and go to the right side of the first stack, like first tree, and left side of the second tree. And if it's less than x, then you need to pop out the first element of the stack 1 and go to the right side. Okay, right side is what you'll be finding the greater than elements, and if it turns out to be greater than the target, this whole sum, pop out the top element from the BST2 and go to the left side, so that you'll be finding some element that's less than the greatest element, so that you can compensate to the target, so or x. So that is the main approach here. So yes, this works. So if there are any doubts, please feel free to comment in the comment section. I hope I've cleared all the concepts. I explained the deep grassroots levels, and I will use the most unique solution, like the stacks thing. I don't think like anyone would use this, like many of them, I feel. So this is one of the most unique solution and efficient solution without using a map or something. So that's it. So that's it for the day. And if there are any doubts, please feel free to comment in the comment section. I'll definitely revert back and reply to your doubts. So if you're not able to understand at any point of time, do the dry run. Please do that using a pen and paper. Do all the things that are there in the code. Do it on yourself. You'll definitely understand it. Okay. So this is one of the method that you must definitely know, so that you can enhance your problem solving skills. So that's it for today, guys. Thank you for watching. Stay tuned.